Michailidis, current chair of the second Young Members Subcommittee. And today I have the pleasure of welcoming you to our lunchtime webinar on dynamic soil structure interaction and damage detection for offshore wind turbines. Before we begin, please let me go through some housekeeping rules and important information. So I will first kindly ask you to keep your video cameras off and microphones on mute for the duration of the presentations. After our two speakers finish with their presentations, we will have some time for a question and answer session. But in the meantime, please feel free to type any questions you might have in the chat. Please also note that this seminar is being recorded and will be later uploaded on our second YouTube channel. And therefore, by dialing into today's event, you consent that any views or information you share will be made public. Moving on, I will now introduce our two speakers. So our first speaker is Michailidis, a dynamic professional currently working as a marine and infrastructure division technical engineer at Archirodon in Greece. He holds an MSc in earthquake engineering at Imperial College London and a Master of Engineering in Civil Engineering from the Aristotle University of Thessaloniki. Michalis has been involved in a variety of projects in the UK, Greece, and Middle East across his career while being in the UK and Greece. And he's also currently an elected member of the second Young Members Subcommittee in the UK. Our second speaker is Dr. Luke Prendergast, who is an associate professor in civil engineering at the University of Nottingham in the UK. He specializes in damage detection for civil engineering infrastructure and offshore wind foundation engineering. Prior to this, he worked as a postdoctoral researcher at the Faculty of Civil Engineering and Geosciences at Delft University of Technology in the Netherlands. He obtained his PhD at University College Dublin in Ireland in 2015 and holds a Bachelor of Engineering from University College Cork in Ireland in 2011. He also works as an assistant editor at the Elsevier Journal of Sound and Vibration, with focus on research related to damage identification in civil engineering structures. His current research interests include structural health monitoring, vibration-based bridge scour monitoring, vehicle bridge interaction, and offshore wind foundation engineering. So without further ado, I will hand over to our first speaker, Michalis, to begin the talk. So Michalis, if you can kindly share your screen now.
Definitely, yeah. Thanks, Evangelos, for the introduction and for inviting us to this lunchtime session. So just let me know if you can see my screen so I can start with that. I will close my camera as well for reasons.
Yeah, that's perfect. Yeah, we
okay.
can see your PowerPoint slides now. Yep.
Perfect. So to begin with, the current title of this presentation will be the design of an offshore wind turbine in North Aegean. This has been a research that I and my colleague Athanasios Petridis conducted earlier in the Aristotle University of Thessaloniki under the supervision of Eva Georgaki. And I will start with the structure of the presentation, giving a quick induction on the onshore and offshore wind energy market. Moving on to the offshore, why we need to go to the offshore wind. Later, I will present the case study with the title and ending with the conclusions and some future points as well. So the wind energy has been the dominant renewable energy resource across the last decade, and you can see the increasing trend on the right hand, comparing this to the other types of energy and renewable energy as well. There are both onshore and offshore applications, while this has been significant in the achievement of the 2020 energy targets and consists the basis for the achievement of the 2030 and 2050 energy targets. In this slide, you can see the new installed onshore and offshore wind farms across Europe during last year, where it is worth mentioning that the UK has been the big player in this table, having almost half of the total installed wind turbines and the most significant amount of the offshore ones. In this case, Greece is not mentioned. I'm referring to Greece because this study is referring to a case study in Greece. So this is something that I would like to mention here as well, because as you can see here on the right hand, there is no electricity demand covered by offshore wind in Greece. All of the applications, all of the electricity demand comes from onshore wind, and this is something that is going to change the next year due to the legislation framework that has been released last year. On the other hand, the UK has almost half of the demand by offshore wind and the other half from onshore one. And you can see on the left hand the trend in both offshore and onshore wind installations across the last decade as well. These statistics are coming from Wind Europe for further reference. At this slide, we are going to demonstrate why we need to go far from the coast. On the right hand, you can see the available aerodynamic field across Europe, and can see that the North Sea and seas around France, north and south, and southeast Mediterranean of Greece has the most significant aerodynamic field across the area of Europe and the UK. The reasons why we should go offshore is that start with the available space that we have for both installation and operation. We can ensure safe distances between the wind turbines, avoiding the wake effects between themselves, and having a clear wind profile each time to be fully exploitable. We can avoid optical and acoustical disturbance from the wind turbines, while we can exploit as well the winds with high density, which are increasing as going far from the coast. You can see on the bottom right hand that the effects of the landscape from a rural environment and a city environment are becoming less significant in the offshore environment. So we can reach the required wind speeds in a smaller construction height. So this brings the required this benefit for the total height of the structure that becomes shorter than the one that we should have onshore. So these points confirm the trend why we need to go to deep waters if we want to go to larger wind capacities. There are a couple of gravity-based cases that are implemented across the last decades. The most favorite one is the monopile substructure that you can see on the first side. There are also tripod or jacket steel structures, while there are concrete ones in the right hand as suction caisson or gravity-based ones. On the other hand, there are some floating offshore wind turbine concepts. The spar type has been the first one to be implemented, like the High Wind project, the pilot one in Norway, and later around the UK. We have also the tension leg platform and the semi-submersible concepts for reference. At this slide, we can see the evolution of wind turbines across their height and their power production as well. So across the history, you can see that wind turbines are becoming bigger and bigger, reaching almost the height of the Shard in London at 300 meters in order to achieve a 14 megawatt wind power production at the moment. While on the right hand, you can see that the wind turbines are becoming larger and larger as going to the deep waters, starting from the land-based ones, moving to monopiles at 30 or 40 meters depth water, later jackets until 70 or 100 in some cases, depending on the soil conditions, and later to the floating concepts. And moving now to the case study, which is the title of the presentation, Design of an Offshore Wind Turbine in North Aegean. This was based on the previous strategic plan of 2015, where there were a couple of locations as presented in the map on the right hand provided. This strategic plan had some key milestones that we should refer to. So this plan was based on the monopile technology at the moment that this has been established, and as being the favorite option, these locations have been selected as suitable for the monopile foundation. Another restraint was the distance from the shore, which had a maximum distance of 6 nautical miles. And so we should reach shallow waters. The available aerodynamic field for these locations, and of course more environmental, historical, and climate change criteria that can be found later in the recorded video. Moving now to the parts of an offshore wind turbine with a monopile foundation. This can be deconstructed to 3 main parts. So we can have the monopile in the substructure, moving later to the transition piece that hangs both the monopile and the tower of the wind turbine. So the tower has been part, and on the top of the tower we're reaching the RNA assembly, which consists of the rotor, hub and blades, plus the nacelle assembly. The loads that we should account for this design are the wind profile that follows an exponential distribution, hydrodynamic loads and hydrostatic loads as well, currents, waves, ice, and of course seismic if being in a susceptible environment. Moving now to the gross properties chosen for the NREL 5 megawatt baseline wind turbine. You can see on the left hand the technical description. So we have a rating power of 5 megawatt, a rotor diameter of 126 meters. The hub height is leveled at 93 meters above the mean sea level. The cut-in speed is at 3 meters per second, rated speed at 11.4, and cut out at 25 meters per second. So across this area, the wind turbine operates in the power control, while when moving from the rated speed to the cut-in from the rated speed to the cut-out wind speed, there is a transition from power control to pitch control, where each blade rotates about its own axis from 0 degrees to 90 degrees, where this goes later to the idling mode. During the pitch control, the wind turbine operates a constant wind power production of reference, which in this case is the 5 megawatts. Another key point is the mass of the rotor on the top of the tower, which has 350 tons, which is almost the same amount as the weight of the tower, just to have a reference point for the dynamic analysis that will follow as well. So regarding the selection of the natural mode characteristics, the design of the natural mode should be between the ranges of 1P and 3P as the optimal scenario. 1P and 3P ranges correspond to the effects of the operational loads and of 1P, which is the frequency at which the rotor completes a full rotation, and 3P is the respective one that each blade reaches the position of its next blade. So in case the natural frequency of the wind turbine is across any of these lengths, there is a significant hazard of excitation that will cause severe problems in terms of serviceability and fatigue as well. In case we have a very stiff design after 3P, this will be a very stocky structure that will be too expensive. In case we have been in a very slender one on the first area before the 1P, this will be susceptible to serviceability issues, and that will be vulnerable to fatigue as well. So this is why the optimal one is between 1P and 3P. In order to be suitable as well for an uncertain site. The fundamental eigenmodes are these two, which is the fore-aft eccentric to the axis of the wind turbine, and the side-to-side, which is symmetric across the axis of the mass. We are using the Campbell diagram in order to prevent the resonation hazard. So you can see that 1P and 3P frequencies are not matched with the natural frequencies of the wind turbine across the rated in between the ranges of the rotor speed corresponding to the rated speed and the cutout speed, which is very important. And the tools that we are using for this design workflow are coming from the NREL, National Renewable Energy Laboratory. We're using the FAST code, which is based in Fortran in order to conduct our numerical analysis, time history analysis, the TurbSim for the generation of the aerodynamic field and B modes for the eigenmode analysis, LPIL for the soil structure interaction, utilizing distributed across the penetration length nonlinear uncoupled horizontal springs with respect to PY curves, according to the API regulations. For a sandstone case, for the current study, because of the site selection position 6 east of island Limnos that I didn't refer in the map. And the standards that we're referring to are the API, the DMDGL, NORSOC, and IEC. Coming now to the design workflow, we are collecting initially the wind data that we are importing to the TurbSim in order to generate the wind field. Later, we have the wave characteristics and the offshore wind turbine properties that we are importing simultaneously to the fast fixed monopile model. We're running the time history analysis for the fixed model initially in order to obtain the applied load combination at the time moment of the maximum bending moment on the mud line. Later, we're obtaining the set of the applied loads that we're applying on the head of the pile using LPIL software that we have already set the respective PY curves for the current study of the sandstone case. In order to obtain the spring stiffnesses, KI, that we need later to import to the B modes in order to conduct the eigenmode analysis and receive the coefficients that we need to import later to the fast monopile model, including the soil structure interaction, using, of course, the initial parameters that we have already used, but corresponding now to the full penetration length and the respective properties for the case study. Once we conduct again the analysis, we can check our structure against the serviceability, strength and fatigue checks that we need to have. If everything is fine with our checks, then the design is complete. Otherwise, we need to return back to the selection of the eigenmode characteristics, the offshore wind turbine properties, and repeat the process. To start the selection of our properties, we're running a preliminary selection of piled tower characteristics, starting with the constant diameter of 6 meters for the monopile and 60 millimeters thickness that get reduced in the towers based at 27, having the 6 meters in the transition piece, and in the tower tops we have in smaller values for both the diameter and the thickness. We're obtaining these two values for the first fundamental eigenmodes, and we're selecting two specific load cases according to IEC standards, where we're using normal turbulence mode for the cut-in speed at 11.4 and 18 meters per second wind speed, which is in between the cut-in, between the rated and the cut-off wind speeds. This way we can select the optimal penetration length to continue with our final design checks later with respect to the eigenmode and stability analysis. Regarding the stability analysis, we need to refer to some key serviceability criteria like the pilot deflection, midline deflection, pilot rotation, and the existence of vertical tangent according to the DNVGL regulations. And the API, on the other hand, suggests a 10 times the diameter penetration length as suitable one, but by this study, we can suggest that we can reduce the penetration length to 5 times the diameter in order to ensure the serviceability criteria that we refer to and still be in between the ranges of 1P and 3P natural frequency that we need to account for in order to avoid any potential excitation. Moving now to the ULS design, we still use the same wind speeds, but moving to extreme turbulence mode, where the wind is the dominant action, and we're maintaining the last combination as before, where the sea wave is the dominant one. We're conducting the time history analysis for a duration of 10 minutes. And you can see on the left hand the wind series that for the first, for the cases that we have the 18 meters per second, we have these fluctuations on the left hand. The blue one gets bigger values due to the extreme turbulence mode, while the green one has smaller values as being the normal one. Both of these cases are those providing the constant power production of 5 megawatt, which is the power production of reference. And the red one, as you can see, corresponds to the 11.4 that has other fluctuations here, smaller than the cut-in speed, being in the power control instead of the pitch control, and having this fluctuation in the wind power production as well, which is smaller than the 5 megawatts. At this slide, we are using the power spectral density referring to the bending moment diagram at the mud line in order to have a qualitative inspection of the performance of the wind turbine. As we previously noted, the natural frequency for the fixed model was at 0.26 hertz, which corresponds to this location here, which is the first significant peak. This is a reason why we have the design between the 1P and the 3P range. If our natural frequency was in between the borders of 1P or 3P, this amplification factor would have been very, very significant, and we should experience excitation issues. Similar-wise, for the power spectral density of the shear forces, there is a significant peak at 0.08 Hertz, which is matching the frequency of the sea waves of interest as well. In this slide, we can have a comparison between the bending moments across the whole structure, including the penetration length and the top of the tower, and on the right hand with the shear forces as well, where we can observe that the most critical points are right underneath the mud line surface, below across the penetration length. So this is something that the soil structure interaction is significant to account for, because otherwise we should have not been able to understand this behavior of the wind turbines. At this slide, yeah, I will skip this one quite quick, because we want to present the significance of the hoop buckling check, which is a check of due to the hydrostatic pressures in the mud line as well, but this is not that significant. I'm a bit concerned about the time. Moving to the fatigue limit state, we have used a Weibull distribution of the wind speed at the hub height. So initially, the distribution was more leveled, but the wind distribution that we had at 10 meters above the mill sea level needs to be transmitted to the hub height, and this is why we have these steps in the distribution with this offset on the left. We're using the M-life of an REL with an ultimate load of 747 meganewton meters in the base of the mud of the wind turbine in the mud line. And we're designing for a life period of 20 years using a Wheeler factor of 5. Regarding the load cases that we accounted for, we're increasing each time the wind speed of reference by 2 meters per second until reaching the 25 meters per second, where the wind turbine goes to the idling mode. And this is a slide describing the damage equivalent load for the list of the load cases in order to understand their magnitude. But we need to weight these damage equivalent loads according to the frequency and normalize them to the most severe one. So we can understand this way that the most significant load cases for the fatigue limit state are those around the pitch control values, and around the transition from the power control to the pitch control actually values, where this is the reason of the fatigue limit, of the fatigue being susceptible to this transition from the two modes of the wind turbine. And for the current study, the predicted time of life has been estimated at 25 years, which has been more than the required one. So concluding, we can suggest that the optimal penetration length can be reduced to 5 times the diameter instead of 10 times the diameter, according to the API, which is a significant and sustainable saving for this case. This rate can vary from 5 to 6 times most of the cases, depending on the soil profile. We can have an efficient design between the 1P and 3P eigenfrequency limits. The most critical structural point has been identified right underneath the mud line. There are sufficient utilization rates according to the NORSOC regulations, while there is evident influence of the pitch control to the development of the applied loads. And we have observed that ULC1, which has been the 11.4 meters per second with extreme turbulence mode, has been the most critical, as we noticed in the moment distribution profile, where the absence of where we have the transition from the power control to the pitch control. While for the fatigue limit state, the most critical design wind speeds have been those around the rated speed of magnitude where the pitch control is activated. And some future comments are that there will be more and more offshore wind turbines across Europe and the UK in order to achieve the 2030 and 2050 energy targets. Crown Estate is leading those projects in the UK, while legislation frameworks are being released across the Mediterranean Sea, so more and more countries are getting involved in this. While next week there will be the COP28 climate change conference in the United Arab Emirates, so there will be significant feedback in this conference regarding the future of the renewable energy in general, and of course the offshore wind one. So we would need more and more engineers to be involved with this type of structures, and hope to help the society achieve the 2030 and 2050 energy targets. Thank you very much for your time and your attention. I hope you enjoyed the presentation. And of course, if you have any questions, we can discuss further at the end of it.
Thank you very much, Michalis, for this very insightful case study. Now we'll move on to the next presentation. That's Luke. Luke, could I please ask you to share your screen?
Yeah, I'll give it a try now. Just
can I also please? Yes, can I also please ask you to keep your camera on for the duration of your presentation, if that's okay?
Can do. Yeah, no problem.
Yes, thank you very much. Thank you.
Can you see the screen?
Yes, we can.
Okay, I'll just get started.
Yeah, the floor is yours.
Okay, so
thank you.
Yeah, thank you very much for the invite this lunchtime to give a small talk on some recent advances that we've been conducting here at University of Nottingham and with many collaborators in damage detection and dynamic soil structure interaction, specifically for offshore wind turbines. So given the time constraints, I've curtailed this down somewhat, but hopefully I can cover some interesting things. So just bear with me for a moment. Okay, so as we know, and as has been mentioned in the previous talk as well, wind turbines are getting larger all the time. This is concerning in one respect because it now means that we need to be very careful about the dynamic response of these structures. So just to show a schematic which was made by a PhD candidate, Jack Todd-Buswell at Nottingham Centre for Geomechanics, this gives an idea of the various loads that act on a wind turbine. We have our environmental loads, the rotor loads, the blade passing loads, wave loads. And if we look at that on a frequency spectrum, we generally try and avoid the various excitation frequency by designing our structure to have a natural frequency between our rotor and blade frequencies. But the problem is that as wind turbines get larger, the natural frequencies tend to reduce and all of these various excitation frequencies tend to compress. So we're getting to a critical point now where this is a particularly governing situation. So I want to talk a little bit about dynamic soil structure interaction. So with an offshore wind turbine, effectively it's a large cantilevered structure with a rotating mechanism at the head. They are fixed to the soil, which is obviously a stiff medium, which can have a variety of constraints on the structure. And then you can get damaging actions like scour erosion occurring, which also changes the boundary conditions. So generally, we will model these as beams on springs if we're doing a simplified design. So I like beams on springs because they're reasonably straightforward to analyze. And also it allows us to include the stiffness and mass contribution of the dynamic parameters. So if we simplify a pile within the soil to a beam spring model with sprung masses, we can generally simply predict its dynamic behavior. Just to give you an indication of what I'll be talking about, if we were to inform the model using the stiffness of the ground informed from some data, for example, cone penetration test data, this is something that we need to be able to estimate accurately, and the inaccuracies in this can lead to certain issues. So one of the things I want to talk about now is a model updating approach that we've developed in the last number of years that can aim to estimate the operational stiffness and mass contribution of the ground in the dynamic soil structure interaction of laterally vibrating piles. So I'm going to talk about that. So the question I'm going to answer here is, can we model the initial stiffness of piles at small strains? So really simple question, not a very simple answer. So this is something that I did during my PhD a number of years ago at University College Dublin. And in effect, what we did was we excavated some piles that were installed at a dense sand quarry site southwest of Dublin in Ireland. And then we basically impact tested them by hitting them with a modal hammer and measuring the dynamic response with a number of inclinometers. Now, you also see in this image some other infrastructure for load jacks and displacement and inclinometers. This was part of a larger testing regime that I won't discuss today because I don't have the time to do so. But if we focus on this bottom left image, we'll see that effectively it's impacting the pile with a modal hammer, which allows us to estimate the time duration of the force, and measuring the output acceleration from accelerometers placed on the system. Now, the idea is that we model the pile as a series of beams and springs, and then we try to estimate the frequency response using a variety of available equations from the literature that purport to be able to give us the small strain response. So the first question is, how do we inform the soil structure interaction? So we use the multi-channel analysis of surface waves method to determine the small strain shear modulus and Young's modulus from the shear wave velocity profile. And that gives us a depth variable small strain Young's modulus profile. Now, the question is, how do we inform springs, which are basically called Winkler springs, using these approaches? So we did a literature survey. This was a number of years ago, and it yielded that there are a number of different equations we can use. So I'm going to discuss those momentarily. But before I do, I want to give you an indication of what the data looks like when you impact test a pile. So first thing we did was just place accelerometers on the pile and then switch them on and just ambiently measure the vibration response. Now, this signal here is an ambient signal. So basically, we can actually see the noise bands for anyone who is interested in signal processing. The excitation was from wind and construction machinery basically moving around the site, and it gives this very low level ambient excitation. So we measured 200 or 300 seconds worth of signal, and then we simply analyze it with frequency domain decomposition, which is a form of using Fourier transform analysis. And we can see that we have a natural frequency somewhere around the 21 hertz peak, which was quite clear for the first natural bending mode of the pile. We then impact tested the pile. So I used the modal hammer. We get a much more clear transient signal, which is dynamically oscillating. We pass that through a frequency response function using the input and output data, and we get these three frequency response function peaks for the three accelerations, approximately at 20 to 21 hertz as well. So this was the data we were using to try and estimate the dynamic response. So what it actually looks like is the following. We impact test the pile, and then we get our output acceleration and data. We turn that into a frequency response function, and then we numerically model the pile as a beam spring model, and we inform the springs using 5 different equations that we extracted from the literature. Okay, so the 5 different equations are by Bayat, Vesic, Salvadori, Meyer-Offenbach, and Kloppel and Glock. They were from the literature around the idea of infinite beams on elastic media, or also buried pipelines or conduits. So the idea is they all look fairly similar, but they're all slightly different. So they all require us to input geometric data about the pile, the diameter, for example, the small strain Young's modulus profile of the site, as well as some information about the pile flexural rigidity in some cases. So when we did that, we basically developed 5 numerical models of our pile. We impact tested the pile, had our experimental data, and then we estimated the predicted response versus the actual response. And we ended up with the following graph. So what this graph shows are the 5 different predictions against the experimental data. So the experimental frequency is 20.26 hertz. That's in heavy black in each line. And the other curve is the numerical prediction in each of these cases. Now, the first thing we noticed was that each of the numerical models overestimates the frequency response, and it also underestimates the system mass. So for those who are familiar with frequency response functions, the height of the peak in the acceleration FRF is related to the mass in the system. So this is an underestimation of mass. So this was a critical finding from my PhD at the time, actually, because it led us to believe that we generally put spring beam models without any incorporation of the soil mass. And actually, the soil mass does appear to be mobilized to some extent. So therefore, if we incorporate that, we should get a better estimate. So that led us on to the development of an FRF-based model updating approach. So this was the next question. Using the FRF, the frequency response function, can we estimate the operational stiffness and mass? So we developed this approach that allowed us to develop a numerical model of a pile using beams on springs. Then we need to input an initial estimate of the stiffness and mass. Now, the stiffness is straightforward because, like any geotechnical design, we use our available resources. So either the small strain shear modulus profile from multi-channel analysis of surface waves, cone penetration test data with a variety of correlations or otherwise, and that would allow us to get stiffness. For mass, we didn't find very much evidence of a way to estimate how much mass is actually mobilized. So what we started off with is taking the pile mass itself, multiplying it by an arbitrary number and distributing it amongst the springs to see if that could be updated effectively. So this is the part where we apply guess weightings. Now, weightings are where we weight the profile of stiffness and mass to give us a starting estimate in a model updating approach. The stiffness weighting is 1 initially, so we assume that our initial guess for our operational stiffness is correct. And the mass weighting is an arbitrary number between 0 and 30 times the pile mass. So 30 is arbitrary. We use that based on the findings from the analysis. We then assemble the numerical model by building the stiffness matrix and putting the springs on beams. We calculate a frequency response function from this model, and then we simply compare this to the one from the real pile. If the frequency peak and its location match, then we end the model. If not, we go back and we update the weightings. And we do this iteratively until such a time as everything matches, and then it ends. So I'm going to demonstrate that a little bit with a numerical prediction, but also with actual experimental data in the next slide. So on this slide, what we see is an example of the updating approach. So we have our actual pile. We've got our numerical model. This is an example of what the first mode of vibration should approximately look like. Then this is a schematic which shows us what the frequency response function of the actual system is. This is the first predicted one from the calculated one, and the idea is to minimize the difference in the peaks. So the objective function is to minimize this difference. So the first prediction from a numerical set of analysis, we created some virtual experimental data where we knew the properties. So we knew what the actual stiffness was, we knew what the actual mass was. And the idea is we tried to see if our numerical method could predict that. So the black line is our virtual experimental data, and the dashed gray line is the first estimate of the response. And as we can see, we significantly underestimate the frequency, which means we are likely overestimating the mass and underestimating the stiffness, or a combination of that. In the next iteration, I'm just going to press the button here, we get a slightly closer prediction, but still it's quite far away. So we use an approach called linear projection, which allows us to try and minimize the objective function in this iterative approach. In the third prediction, we get a much closer prediction. And finally, in the fourth prediction, we get an exact match. Now, I am eager to say that this is numerical data, which is perfect, noise-free. We did also add some virtual noise to see how that would work, but this is just to give you an idea that this approach can work. So this was actually published in the Journal of Sound and Vibration a number of years ago, and the papers are available online. So the next question was to look at how this looks in terms of kind of minimizing objective functions, or looking at the pathway towards convergence. So what you see in this plot here is your target stiffness weighting. What we did was we inputted a cone penetration test data of virtual data for a medium dense sand. We multiplied that value by 0.75. Then we put in the actual profile, And these gray lines show the number of iterations it takes to achieve convergence. So all gray lines start off as 1 times the predicted profile, and eventually they all converge on 0.75 times the profile, which was the target data. This is an example of 10 separate runs. Similarly, this graph is for the mass weighting. So what we did was we took the pile weight, multiplied it by 5, and distributed it amongst the springs. And the model starts off with some random estimate of the mass between 0 and 30 times the pile mass. And eventually over 2 to 3, 4, 5 iterations, etc., everything converges on the target value. So this worked really well in a numerical controlled environment. And for a series of 10 runs, the percentage difference between our converged values, so the estimated values, and the actual values was less than 0.5% difference. So that gave us an indication that the model should be able to work on real piles, which is what we did subsequently. So can we do it for real piles? So at the same dense sand test site that I had shown a moment ago in Blessington, southwest of Dublin, we had 2 piles installed in the ground. So I've shown them schematically as one for space saving in the paper that this is in. One of them was embedded. They were both embedded 7.2 meters originally. One was then excavated so that it had 4.5 meters of embedment, and the other was excavated so that there was 3.1 meters of embedment. The purpose of this was to see if the results worked for 2 different L/D or slenderness ratio arrangements without changing the diameter. Okay, so we developed 2 numerical models, B and C. So this is for pile 1 and this is for pile 2. And what you see here is the location where I actually inputted the modal hammer impact, so that we could physically model the exact scenario corresponding to an impact test from the real data. So here's an image of me actually impact testing it. So we impact tested the pile at a location, we measured the response, and that allowed us to get the frequency response function, which we used as the target in the prediction. And then we started the idea of saying, okay, let's see if we can actually predict the real operational stiffness. So this was quite interesting. The experimental data for both piles is as follows. The top graphs are the frequency response of the hammer impact and the frequency response function, which corresponds to the input and output accelerations for 5 different impact tests. So we did 5 to ensure that the method was repeatable, and we get a reasonably consistent frequency response function across the 5 tests. The second second row here of data are for the other pile that's embedded 3.1 meters. So again, this is the frequency response of the hammer impact. This is less important, but it's critically we had a very consistent frequency response function across the 5 impact tests for the second pile. So this was our target data. It was reasonably clean, but it was real data incorporating all of the issues that sensors have, including noise and all of those problems. So we input this into our model and we tried to see if we could estimate the stiffness. So this is to give you the data just to show how consistent it is. You've got P1, T1 to T5. They're the 5 tests. The frequency was between 20.26 and then consistently 20.02. It's important to note for the signal processing people in the chat that the signal was only 3 seconds long, so there was a reasonably not so well-defined frequency bin, but it worked quite well. The damping ratio was estimated using both logarithmic decay and also an exponential curve fitting approach, and that was reasonably consistent, but a little bit more variable depending on what was happening. So to show you what the results look like, the iterations are as follows. So the numerical predictions all converged within 4 iterations, but it is important to note that we had the exact profile that we knew we needed, and we weighted that. In this particular case, we have the output only data, so the frequency response function, and we are predicting the stiffness from the small strains Young's modulus profile, which was measured from multi-channel analysis of surface waves. So that has some error in that respect. So the first iteration shows that we have our experimental data for the first pile, approximately 20.26 hertz. This is the first prediction of the numerical model. So we underpredict the frequency, overpredict the mass, etc. And when we run it automatically, after 21 iterations, we get a match in the peak data. So the frequency response functions do not match at all frequencies, but they are a very good fit considering it's a numerical one-dimensional prediction of real experimental data. So just to show you what that looks like from the time domain, the first prediction, this is the acceleration signal of the output signal from the top accelerometer. This data was filtered to remove higher order modes. And this is the gray line is the first prediction. So we see that we heavily underestimate the acceleration magnitude. And after 21 iterations, we get a reasonably good, if not perfect match, one could argue, of the numerical prediction on the experimental value. And just to show you what that looks like in terms of 5 different runs of the model for 5 different estimates of stiffness. If we use these 5 different models from the literature to predict the operational stiffness of the ground, we get 5 very different stiffness profiles. So this is something that was problematic because it suggests that the ability to determine the frequency of a pile is actually quite complex. So what we did was we inputted each of these models as our starting guess in the model, and we ran it until such a time as we got convergence. And I was very pleased when I saw this data happen because all 5 of them approximately converged together here, which suggests that this is the actual stiffness that the system feels approximately. So this was quite a positive finding, and these results are published in Soil Dynamics and Earthquake Engineering Journal. Just to give you an idea of what the convergence plot looks like for real data, it takes many more iterations than the numerical prediction, but it does run quite well. So these are 5 different runs, and what we can see is that run 1 gives a mass weighting of 5.63, 6.14, 599, 589, 603, approximately equal to one another. So these mass weightings are the weight of the pile multiplied by the mass weighting distributed to the springs in the model. So it suggests that the approximately, for example, 5.63 times the pile mass is also mobilized as soil when you dynamically impact the pile. That's what this number actually suggests. In terms of the stiffness profile, we started off with a prediction from the small strain Young's modulus, and our converged data was approximately 0.94 times that. So that was particularly close prediction across the board for the stiffness estimation. So that's just a little bit of dynamic soil structure interaction and model updating. I just wanted to include some reasonably recent work that a PhD candidate at Nottingham Centre for Geomechanics, Jack Todd-Buswell, is doing. So we are extending this effectively to the nonlinear range. This is actually an image, and I don't appear to be able to interact with it. It's actually a video. Bear with me for one moment. Sorry, now 1 second. Okay, so hopefully you can hear me again.
Yes, all good.
Okay,
Yes.
Good. All right, sorry about that. So just to show you, this is when we have nonlinearity, when we apply large lateral loads, we get this nonlinear response, and each of the respective springs has a nonlinear response. So in terms of dynamics, when you're in the small strain region, we know that our PY response or stress strain response is approximately linear. However, when we go to larger strains, as might occur under storm waves, for example, then we get this larger hysteretic type response. And that can be something that's difficult to encapsulate as well. So some of the recent work we've been looking at is characterizing this using available site inspection data like cone penetration test data, for example. So just to give you an example of what the response of an offshore system might look like under an irregular loading sequence. This on the left is the soil structure interaction response of a given spring in a numerical model under the action of an irregular load series. This is work that's undertaken, as I mentioned, by PhD candidate Jack Todd-Buswell in his work, which he's recently submitted for his PhD. And it just gives an idea of being able to track the nonlinear, strongly nonlinear soil structure interaction response across a range of values. So the idea is that your PY response is an ultimate resistance, and as the system oscillates within that sphere, it'll oscillate between these bounds across a variety of strain levels. The response here is simulated using a Masing rules type framework. So you keep a record of all of the reversals, and there are a series of bookkeeping rules that are used in this case. When we incorporate other forms of spring, like Book-Wen models, we can actually incorporate other general shapes in your hysteresis response. So this particular case shows the case where we will have a degradation in our reversal stiffness. So normally on the left, we can see that the reversal stiffness has the same magnitude as the initial stiffness. In this particular case, the reversal stiffness is degraded. So this can be predicted using these models as well. These models are also capable of detecting or modeling gapping phenomena, whereby the soil and pile actually separate due to large strain movements, or scour occurrence. So in this particular case, we can see that if a gap forms, your displacement from zero is not affected by the loading. It doesn't actually impose or incur any reaction at that particular case. So these models are in development at the moment, and we're hoping to characterize these using cone penetration test data or other soil structure interaction data. I'm almost at the end, so I just wanted to cover some very recent work as well by some of the researchers at the Nottingham Centre for Geomechanics. Up until now, I've shown soil structure interaction models that are predominantly modeled using lateral soil springs only, PY. However, as monopiles are becoming larger, and in that case, they are getting larger and larger all the time, the actual mechanisms of reaction are changing. So this is an example of a large diameter monopile. This is reasonably rigid or stocky. In addition to the PY response, you actually have a lateral axial friction that's generated due to the rotation of the cylinder in the ground, as well as a base shear and a base moment caused by mobilizing a soil base resistance as well. So this schematically can be shown on the right as PY curves in addition to moment rotation curves, in addition to base moment and base shear curves. This model is currently has been validated against some static data for monotonic loading, and we are currently looking to expand it to dynamic soil structure interaction to account for the various extra mobilized resistances. And just to show you on the final slide here what that really looks like, when we actually load a pile, we expect that we generate this axial uniform, reasonably uniform friction, depending on the heterogeneity of the soil profile, of course, around the pile. However, when you rotate it, you get a variable friction generated across the cross-section. So we can use some of the approaches from CPT-based axial capacity, like the UWA approach or the ICO5 approach, and we try to modify those to generate moment rotation curves. So this is saying what I just said verbally. So under axial loading, we have a uniform friction, and under variable or moment rotation, we'll get a variable friction. So I am conscious of time, so I will end there. I just wanted to say thanks to some of the collaborators, particularly the top two researchers, that they are absolutely super important to this work because they are continuing it. So Andreas Ockham, he's actually continuing the model updating approach to be capable of estimating the embedded length of pile foundations, which may not be readily available, which will be a very useful addition to the structural health monitoring field or damage detection fields as well. So yeah, thank you for your time.
Thank you very much, Luke. It was a really good presentation. Also nice to see experimental test. So I guess now we can move on to the Q&A session. I'm already seeing that there are some questions in the chat. So thank you again both, Michalis and Luke, for the great presentations. I think Michalis has already answered a couple of questions, but Luke, there are two that are addressed to you. That's okay? So
yeah,
the first one, yes, asks, with respect to guessing the mass and frequency, were you able to come up with some empirical ranges, says thumb of rule, to guess as close as possible?
Okay, so the mass and frequency. Try to guess in the mass, were you able to come up with some rules of thumb? Not really. I mean, the problem with frequency response of piles is that the difficulty is knowing exactly what that should be. And in general, you can use design approaches like the initial stiffness of the API equations, or even the more recently developed ones, to try and give you an estimate of that, or some of the subgrade reaction approaches that we've seen. What I did at the time, which seemed like a very straightforward simplification is by using a pile that had a significant amount of pile above the surface, that would mobilize the first mode of vibration quite well. And by assuming a fixed value at the base or a little bit below the surface, you could estimate the cantilever frequency, which is the operational upper bound frequency you'd expect. And once our value was less than that, we knew we were in the right range. So that's basically how we did that at the time. But I am absolutely open to suggestions about better ways of doing it now. But yes, that's the answer.
Thank you. There is another one I can see in the chat right below that. Are the weightings constant values? Are the weightings constant values, or do they vary with depth and/or mobilization of soil progressive shearing?
Thank you, Benjamin, for that question. They're constant values in this work, but Andreas Ockham, who's a PhD candidate, is currently enhancing this to be able to come up with a depth-dependent variable weighting. So the problem is we're using the first mode of vibration predominantly at the moment, and we've been able to extract quite a large amount of data out of that. So by looking at where the frequency is and what the peak is in the acceleration FRF, we can actually predict both the mass contribution and the stiffness contribution. We're currently enhancing that to use multiple modes of vibration to be able to determine other methods. So without using a stochastic or uncertainty-based approach where we come up with a likely variable stiffness, we're trying to come up with a deterministic approach which actually uses multiple modes to give us an indication of the operational stiffness as a variable with depth and the mass as well. So it is work in progress, and I really am hoping that it'll work out quite soon.
Okay, thank you very much. Again, I can see that Michalis has added some questions, as I said before. So there is another one for you, Luke. So you said the height of the curve represents the under-predicting the stiffness and/or overestimating the mass. Could you touch on this again, please?
Yes, so the frequency response function of the acceleration. So we impact the pile, we have a force time history, we get an output acceleration. When we convert that to a frequency response function, the frequency on the horizontal axis is the natural frequency, and the peak is the magnitude of the acceleration frequency response function. That is related to the mass contribution in the system. So the higher the mass, the lower that peak value will be. The lower the mass, the higher that peak value will be. So that's a very simplified version of that, of course. So mass and stiffness both affect the frequency of the system. So the higher the mass, the lower the frequency, higher the stiffness, the higher the frequency. But the actual height of the peak is a function of the amount of mass in the system. So by using that information from the target value, from the actual measured data, by adding more or taking some mass away from our numerical prediction, we would change the height of the peak as well as the frequency. So it's a optimization approach trying to match both frequency and mass, which is why it's an iterative approach. I hope that answers the question a little bit.
Yes, it does. Thank you.
Okay.
Thank you, Francis. Thank you, Luke. I'm just reading through the chat now. So there is one. It's not addressed to somebody specifically, but the question is how to evaluate which type of soil spring definition to use for seismic loads on piles. How do I generate them? Is it possible to evaluate transient damping due to the soil-pile interaction during the earthquake? Not sure who wants to touch on that.
I'm a little outside my comfort zone on the seismic side of things. I prefer not to venture a guess. We have done a little bit of work on this with pseudostatic modeling, but for the purposes of large strain or even small strain seismic analysis, it's a little bit more difficult. So I'm not actually sure.
Michalis, you have any ideas on that?
So, to my knowledge, seismic is not a hazard for the overall structural integrity of wind turbines, of offshore wind turbines, due to the natural characteristics, and the excitation is not a potential scenario with the seismic actions. However, the soil liquefaction is something that should have been considered in cases like this. And it is a completely different study from what myself and Luke have presented, but the influence of liquefied soil to the response of wind turbine is a subject of interest for a lot of researchers as well.
Okay. Yeah, thank you both. I hope that has answered the question to some extent, at least. Another question is addressed to Luke. So it says, hi Luke, beam spring moment model, what is the angle between the moment spring and the horizontal spring? Why is that?
I suspect, I'm going to share the screen. I suspect you're referring to this image here on the right. And if you are, it's a three-dimensional representation of a 2D problem. So there is no actual angle between them. This is supposed to be coming in the X direction, if we look at the schematic up here on the left. So the idea is this is a rotational spring, so it affects the ability for the node to rotate. And this is the horizontal deflection of the same node. So there's no actual angle between them, in a sense. It's just the way that it's drawn. Does that answer the question?
Please feel free to open your mics and ask any questions you want as well while we're reading through the chat.
Hi, Justin. Hi, Luke. Can you hear me?
Yep.
Hello. Yeah. So in the figure you showed, you said it's a 3D configuration, right? So the moment spring should be perpendicular to that plane, where the beam spring located.
Yes, in schematic terms, but actually this is a two-dimensional model. So the way you do it is you impose a constraint, a rotational constraint on the rotational degree of freedom in the beam model. So there isn't really an out-of-plane place where you place this rotational spring, if you know what I mean. It's not a three-dimensional model. If you were modeling this, you would put a lateral spring for the PY and a rotational spring at the same node for the moment rotation. But for the purposes of demonstrating it, the 3D visualization was supposed to be more clear.
Okay. Okay, now clear. Thank you.
No worries.
Yeah.
Then is another one. It's quite a big one. So it says, what is the effect of the diameter of the pile and the length of the pile? So the pile will be rigid or flexible according to the diameter, the length, and the soil. And what is the effect on horizontal spring higher? Says, according to the soil profile, there will be a different dynamic design spectrum. So do we have to avoid a certain type of foundation in seismic zones? And there are a couple of more questions. Maybe if we can touch first of them in those.
I guess I can jump in with the length over diameter part. So the the L over D, the slenderness ratio, generally the way these structures are characterized or categorized, should I say, is based on length over diameter. So if you have a length divided by your diameter greater than 10, we generally term this to be a flexible pile. And if it's less than 10 or less than 6, for example, it's a rigid pile. Now, those definitions vary a little bit. And of course, they are also a function of the soil in which you're putting them. But basically, broadly speaking, if it's a rigid pile, it tends to rotate rather than flex or bend when it's loaded, whereas a flexible pile will tend to undergo flexure as opposed to rigid rotation. So they're not strictly, there's a bit of variability there. I hope that kind of answers the question. So in effect, if you've got a small pile, like a 10-meter long, but it's got a 1 meter diameter, that's got an L over D of 10. And if you scaled that up, it's the L over D that we look at, not the absolute magnitudes of diameter. I hope that makes some sense.
Definitely does. I think the following question was basically if we need to avoid a certain type of foundation in seismic zones.
Again, this comes to the natural characteristics of the system, and you should select each type of foundation regarding the natural the Eigenmode properties each time, in order to avoid potential excitation with the seismic actions, and of course investigate for liquefied soils in these cases.
Okay, to understand it's a complicated question, you cannot give a black or white
Yeah,
answer, essentially.
Yeah, and of course, this
Yeah.
comes again to the type of the soil. If it is a clay or a rock, that will be a completely different discussion.
Yes, I see. No, thank you. There are a couple of more in the same essay. It says, what about the dynamic behavior in offshore, even in some soil such as chalk? I think that's a little bit to the previous one. They're connected. And then what about the dynamic? Yeah, I think it's the same. Yeah. Okay. So let me see if there is anything else on the chat. No. Is there anybody that would like to ask any further questions to our two presenters? Feel free to just type in the chat or open your mic and ask a question directly. I don't see anything coming in, and I think, Michalis, you already answered some of the questions while Luke was presenting. I'm correct. Okay.
Of course,
So,
if anyone has any further questions, please be in contact with myself and Luke, and we will be happy to help you with them.
Yeah, absolutely. Please do. You can find my email address on the internet.
okay, that's great. Yeah, thank you very much both. It was two great presentations for the lunchtime talk. If there is anything else, as Luke and Michalis mentioned, please feel free to contact us in our second YMCMS email. We can redirect your questions on. You can just directly ask your questions to the two speakers. So thank you very much for joining us today. I hope you enjoyed the talk. I definitely did. And thank you again, Michalis and Luke. Thank you very much for accepting our invitation and giving these great talks. Thank you.
Thank you very much.
Thank you.
Have a
Thanks,
nice
everyone.
day.
Have a nice day, everyone.
Bye-bye.
Bye.